We have our laser with our spatial filter and a microscope objective and our collimating lens to make a beam expander. We then have a stop here with which to stop down our laser so we could remove some of the diffraction effects from the pinhole. We have a plane mirror here to bend the light for 90 degrees so we have more path length to work with.
So this is some of the diffraction theory for a situation when there's no lens. So we have collimated light input and then our aperture, which is 2a, a is the radius. And we can use this equation to find the location of the different modes. So this shows at the first mode far away, there it's bright, and then at the next one we found this place where it's dark, and then it's bright again. And this translates to a graph like this. So this is bright, and then dark, and then bright, and then we can continue to repeat until it just gets so close together it's all jumbled.
So for the first part of our lab, we set our aperture here. We determined the aperture radius A by actually setting our Z2 distance to 2 for NF equals 1, which would correspond to the bright spot at the center. We set our Z equal to 2 so we would have a manageable distance that we knew would work, and then back solve for our A, which we got to be 0.044 inches or 1.1 millimeters. We then moved our microscope through to find the first dark spot, which would correspond to NF equals 2. We found that to be at 960 millimeters, and when we plugged in our values to check that into the calculations, we found that it should have been 960, which is close. This is at best focus, and then if we slide it out, we can find a null at the -1.
This is how diffraction works with a system when a lens is present. So we have collimated light on the lens and then the aperture, and then it creates, at the best focus, at the focal point of the lens, a bright spot. And then if we go out to either side, there will be dark spots at the -1, another bright spot, a -2, and then on and on. And this corresponds to this pattern.
In the next portion of the lab, we varied the radius of the aperture and measured where the -1 and +1 Fresnel zones were. We made the aperture larger, and we expected to, and did end up seeing the Fresnel zones, minus and +1 Fresnel zones, get closer and closer to the best focus. This is a graph of the spacing between our Fresnel zones versus the aperture diameter, or radius. So as we expected, as the aperture increases in size, the Fresnel zones get closer and closer together until eventually the aperture would be so large that it essentially wouldn't even be there, in which case they would coincide with best focus.
In the next part of this lab, we placed a lens with 1,000 millimeters or 1 meter focal length, and we followed this up by an aperture, and we wanted to create a diffraction limited system. So we calculated that to do that we needed our aperture to be 7.7 millimeters in diameter, so we placed that as close to the lens as we could, and then we placed a slit at the best focus. We calculated that the resolution of this system, which has an F number of about 130, is about 0.08 millimeters, and so we set our slit width to that, and then we followed it up by a photodetector, and we scanned our slit across our spot and took power readings, and this created our line spread function, which we could then convert using MATLAB into our MTF.
So this is comparing the spot diagrams for the different modes, 0 and then -1 and +1. If we were to look across just on axis, then we would get something like this, looking at the dark spot in the centers. But since what we did is look at the line spread, it's averaging all the energy across a line, it looks something more like this.
So this is the raw data we obtained in the previous part of the lab for +1 defocus, and this is the data once it's been corrected and turned into a line spread function. This is the Fourier transform of the line spread function, or MTF, and so our blue line is our MTF, and so on the edges it spikes because we didn't extend our data into infinity, so you get edge problems in the Fourier transform. But you can see it's pretty similar to the expected MTF, and this is our function plotted against the expected function. So we didn't get the dip in the center, but it's not so dissimilar. This is for -1 defocus, and this is our line spread function. Here our blue is all off to the sides, and so you can see that it's not as good as our previous one, but that happens. And so I think it's because we had fewer data points for this, so it wasn't able to recreate as easily. This is for our at focus position, and here's our line spread function. And here it actually is very close to the expected MTF, and we skip the same edge effects.
We entered our lens system into Zmax and looked at the MTF. You can see that our cutoff wavelength is about 12, which is what we calculated it to be. We then added in defocus to get to the -1 and +1 modes, and you can see that the MTF decreases.